So now we are going to discuss synthesis of aldehydes and ketones using alkynes, and the ozonolysis that we are doing over here is obviously again reductive ozonolysis. So here the middle carbon will be converted to a ketone and the terminal will be converted to a aldehyde. So your product will be R C double bond O and the terminal will be aldehyde, as I said. So this is a synthesis of a alpha dicarbonyl rather. Okay. Now since there is a R in place of a H, so both will become now ketones. Okay. The second one is obviously mercuration of alkynes. Now as in case of alkenes you had added water, so this is also a hydration of alkyne. Now in alkenes we knew it was the synthesis of higher degree alcohol, so just think that you are adding OH to this carbon and the terminal carbon you add H, so the resulting molecule will be, so instead of doing the whole mechanism you can think this way. This is your OH, that becomes your CH2, effectively this is a enol. Just do tautomerism at the step. Okay, now that would mean that this is converted to a COCH3. This is basically synthesis of a ketomethyl. Okay, what is ketomethyl? This thing is called ketomethyl. All right. Again, as in the case of alkenes, we know hydroboration led to the formation of lower degree alcohols. Here also it is hydration of an alkyne, but the addition is just reverse as we have observed in the previous case of mercuration. So here you will be adding H to this carbon and OH to this carbon, which means you will be producing a molecule something like this. Again, if you do tautomerism of this compound, what you end up with is CH2, CHO. Okay. Again, remember in alkenes we had done cis hydroxylation. Okay, so here also this is cis hydroxylation. So for one pi bond there was addition of two OH bonds across the carbons. Okay, now there are two pi bonds in alkyne, so you will be adding OH, OH followed by another OH and another OH. So resulting, you will think that we are adding around 4 OH. Okay, 2 OH per pi bond. So the molecule now you get is C, OH, OH, C, OH, OH and H. Technically this is now what? A gem diol. We know gem diols are unstable. So basically 2 molecules of water from each carbon will go away and that leads to the formation of diketone. So now we have known two methods by which 1,2 dicarbonyls or alpha dicarbonyls can be prepared. One is cold KMnO4, its reaction with alkyne, or you do ozonolysis of alkyne. For this case also, just try to do the similar thing. Again, leads to the formation of a gem diol. Take out the water. And that is your product. We have already covered this, but just mentioning things over here so that you have all the reactions in one particular lecture of preparation of carbonyl compounds from various reagents. So an alkyl nitrile is what? R C triple bond N. Now if you are reacting this with Grignard reagent, which is RMGX, so here you can think this nucleophile will attack the electrophilic carbon and one of the pi bonds will break to maintain the valency of carbon. So here you have R prime C double bond N minus MGX. This is basically an imine that has formed, which is on treatment with or doing acidic workup. It will undergo hydrolysis. And that will lead to the formation of a ketone. Okay. Let us do the same reaction with a HCN, which is hydrogen cyanide. Again, same type of reaction as you have done before. HR. Once we do hydrolysis, leads to the formation of a aldehyde. Okay. Now we are doing the synthesis of aldehydes from esters. Okay. The reagent that we are using over here is diisobutyl aluminium hydride. Okay. Keep a note that this is having only one hydrogen. Okay. So if you're comparing DIBAL-H with lithium aluminum hydride will be having 4 hydrides. Okay, but DIBAL is going to have only one hydride, and the structure of it is something like this. If you have an aluminium, say there is one H, okay, and that is how it looks. Okay, so this is your negative part. Now, so if you're treating this with an ester, since only one H minus is present, say the temperature is around minus 78 degrees Celsius, and you're using a solvent, something like hexane. Okay, so this hydrogen will reduce this, and it will lead to the formation of aldehyde. So reduction is only one time. That is why the reaction stops at aldehyde and it does not further go to alcohol. If you're using lithium aluminum hydride over here, then the reduction will produce alcohol. Okay, so here you're only getting an aldehyde, and besides that you will be getting this alcohol, which is suppose this one. Now if you're using a nitrile, again if you're using DIBAL-H in hexane, since there is only one hydride, so reduction will happen only once. Okay, reduction will happen only once. Okay, and after hydrolysis, so this is followed by acidic workup, you are getting only a aldehyde. Now if you're doing from acid chlorides, okay, what are the acid chlorides? Something like this. Now when acid chlorides are treated with reagents like R2CuLi, it's basically a Gilman reagent. Again, solvent is THF, okay, followed by acidic workup. This particular alkyl group will replace the Cl, and that leads to the formation of a ketone. Another reagent that will be performing the same reaction is R2CD. Okay, again the solvent over here is THF followed by acidic workup, okay, and leads to the formation of this. A very beautiful way of converting acid chlorides to aldehydes will be the use of Rosenband's reduction, in which hydrogen is absorbed on the surface of palladium. Here BaSO4 acts as a support, and quinoline acts as a poison of this particular catalyst, so that the reaction stops at the stage of aldehyde. Another method of making aldehydes from nitriles is using Stephen's method of synthesis of aldehydes, in which what we do, we treat a alkyl nitrile with SnCl2 in presence of ether, okay, in presence of ether and HCl, followed by workup with water, little bit of warming, and that gives you an aldehyde. With the mechanism of this reaction, just watch, because questions related to the mechanism of this reaction may come. So this is having a lone pair once you have added H plus in the medium, so protonation will take place of this lone pair, leading to the formation of something like this. Now SnCl2, this is in +2 state, so it acts as a reducing agent. Alright, gives one electron, leading to formation of SnCl3, which on further protonation will give you NH, H, and along with Cl4, this tin can go to a higher oxidation state, okay, or higher coordination number, not oxidation state, and it will lead to the formation of H. This undergoes protonation, okay, say twice of this, and SnCl6 is another intermediate that is formed within the reaction. Now this will undergo hydrolysis, okay, leading to the formation of where this bond comes back, this acts as a leaving group, alright, and that gives you now the aldehyde. Now, for practice, you can obviously try these two. This is benzonitrile. Once you have treated with this reagent, SnCl2, HCl ether, followed by treatment with water, okay, or you can try something like this. Same reagent, okay. The first one obviously will give you benzaldehyde, and this one will give you an aldehyde group attached to a cyclopropane ring, okay. Now there are two possible reagents that can do this. One is lead tetraacetate, okay, lead tetraacetate, or it can be periodic acid. So suppose you have been given a vicinal diol. You are using either lead tetraacetate or periodic acid. Both will oxidize OH to COH to C double bond O and cleave this bond, okay. This is its function. That's why it's called oxidative cleavage. And so the molecule that will be formed will be two molecules of aldehyde. All right. Now, again, this is another method by which alpha di, better to say carbonyls, because it can be ketones and aldehydes both, can be synthesized is by using selenium dioxide. It's a very good reagent. Selenium dioxide looks like this. Okay. So if you're given a molecule something like that, CHO, then the alpha carbon will always be converted to C double bond O. Okay. So that means the product for this reaction will be something like this. So in today's class, I think we have studied three methods by which we can prepare alpha dicarbonyls. Okay, there are certain things that you should know additional apart from this. Some rules I'm giving you. First one, I have mentioned already over here. The second part is it oxidizes CH3 group preferentially over CH2 group. So if there is a competition between CH2 and CH3, it will oxidize the CH2 group over CH2 group. Point number C, it can also be used for the synthesis of allylic alcohol. Point number D, it may also cause dehydration. Okay, so far we will only be concentrating on the first 2 points, that is A and B. The other 2 points, they rarely these questions come at your level, that is of IIT, JEE or NEET. So I have given you problems that are dealing with the first 2 points. Over here, what will form? This is a CH3. So obviously, knowing the name of this molecule is very important. This is called glyoxal. Now here also you have a CH3, here also you have a CH3. So either one you oxidize. This is called methyl glyoxal. Now here you have a CH3 and here you have a CH2. So obviously second rule says it will not be reacting with the CH2 but will be reacting with the CH3 to give you this. Now this compound can be converted. So here is your alpha carbon. So it produces something like this. This is your alpha CH. So it will be producing something like this. If you are given, this is called acetophenone. Now this will be converted to something like this. All right. So just choose the alpha carbon and make it C double bond O. The next one we are doing is called Oppenaur Oxidation. So it's basically used for oxidation of secondary alcohols with using acetone and aluminum alkoxide, such as this OBUT is basically tertiary butoxide. So this is basically aluminum trialkoxide. Okay. Now, the general scheme for the reaction is R2CHOH is your 2-degree ol, which will be oxidized, okay, to a ketone. Now the reaction is reversible. That's why we are using this particular arrow. The ketone used, as I said, is acetone, and that is your catalyst. Okay. This will undergo oxidation and this will undergo reduction. Okay. So that means we will be producing something like this, and the alcohol will be formed. The name is, okay, now everybody knows this is a sanitizer, so this is your isopropanol. Okay. Another thing important should be noticed, okay, that is primary alcohols can also be oxidized to aldehydes only if parabenzoquinone. What is parabenzoquinone? Looks something like this. Is used in place of acetone. Okay, that is what will be formed. So stoichiometrically, the reaction, 3 molecules of this will be oxidized to produce 3 molecules of ketone, and 3 molecules of acetone will be reduced to produce 3 molecules of this thing. Okay. Or it is better to write. This is forming Al. Okay, let us remove this part. Don't need this. Now, mechanistically, here we have R2 okay. Now how this is formed? ये कैसे बना? What happens is 3R2CHOH will be reacting with OBUT whole thrice to form R2CHO whole thrice and BUTOH. So just the alkoxide is getting exchanged over here. Then this molecule is going to react with acetone via a 6-membered transition state, which is, as I'm writing over here, we have a C double bond O, here you have the Al, Cr2 whole twice. Now this particular aluminium, we know it is like a Lewis acid, so the lone pair will be interacting with this aluminium, and we have a bond over here, basically an adduct. Now this hydrogen that you see over here, this is reducing the aldehyde. Okay, so basically this is a hydride transfer from the secondary ol to the ketone. Okay, so here also this is the hydride which is going to react with this, and that gets opened up. Okay, and this bond now breaks and comes over here to form the ketone. So that means, so this is going here, that means we will say the product that we are getting now is R2C double bond O, which has lost the hydrogen, plus CH3 whole twice CHO. This is the bond with aluminium which already has Cr2. Now if this particular thing reacts two more times, so with whom? Acetone. We will eventually get the catalyst back, that is CH3 whole twice CHO whole thrice Al plus 2 more molecules of the ketone. Okay. Another important thing about this catalyst is it is used to oxidize unsaturated alcohols, because this particular reagent, the catalyst, it does not react with the pi bonds. Okay, the catalyst does not react with the pi bonds. So let us take some examples over here. Just erasing this thing. Suppose I've given you and said you are using Al, BUT whole thrice, acetone, some heat. So obviously this will get oxidized to this. Okay, this is reaction number 1. For reaction number 2, I'm giving you so only this portion is getting oxidized, right? So rest of the molecule remains the same. Okay, don't need to get panicky about what is other than the secondary alcohol. Nothing will happen there. So this is your product again. Just giving you another one. That gets oxidized too. Okay. The next reaction we are doing is called Pinacol-Pinacolone rearrangement. Now, what is Pinacol? It is a vicinal diol. Okay. This, when it is treated with H plus, the product that is formed is something like this. So this is Pinacol, and that is Pinacolone. It is an acid catalyzed reaction. The mechanism can be given as such. Just have a look. I have always told you that whenever you have OH, NH, or any atom having a lone pair, okay, except the halogens, okay, if acid is added to the medium, use one of the lone pairs and protonate that group. So here I have protonated the O to OH2 plus. Now OH is not a very good leaving group. We have studied these things, but water is a good leaving group. Besides, positive charge is not stable on oxygen, so this bond will break up, leading to the formation of a carbocation, which is the RDS. And now what will happen? A group from here will now migrate to this portion so that this is stabilized, this carbocation is stabilized. So here a methyl migration is happening and something like that will be formed. You have a OH, lone pair from here will come and satisfy this charge, leads to the formation of something like this. You have a methyl, proton transfer reaction will take place. Obviously with the solvent, something like water, and this is your Pinnacle. Okay. Now here is something interesting about which group will migrate and which will not. Okay. So the migration order, irrespective of symmetrical or asymmetrical alcohols being used. Doesn't matter whether you're having a symmetrical alcohol or asymmetrical alcohol, right? Now that is H, that means H minus will be greater than aryl minus, then alkyl minus. Okay. If you're only considering the aryls, so with the aryls the order is P-anisile greater than toluyl, which is greater than phenyl, greater than parachlorophenyl. One thing to note over here is more electron rich aryls have greater migratory aptitude or migratory power, using a more simpler language. Okay, so let us do some problems. Now this is a symmetrical alcohol, diol actually. So again, if you do the protonation part, what happens is you get something like this. Now again, proton transfer has taken place in this step. Carbocation formation, okay. Now what we have studied, if it is H, aryl and alkyl. Me is an alkyl, H is not an alkyl, so H will be having greater migratory aptitude. So H will migrate instead of Me. That means, so this is H minus shift. That means we are going to have Me plus Me. Lone pair from here goes in here, and also we can think proton loss is also taking place at the same time. So we're doing both the steps in the one single thing. So we're getting this type of a thing. Now here we have to first think where, if I protonate, a stable carbocation will form, right? If you protonate on this, then charge over here will not be stabilized because there is nothing to stabilize. Hydrogen cannot impart or use plus I effect, but if you make positive charge here after protonating this, as I'm showing, if this gets protonated, then once it goes away, you're having a plus charge. So this is stabilized by the plus I effect. Stabilizes. So in case of unsymmetrical vicinal diols, water will go from that part where it leads to more stable carbocation. Okay. So I'm writing this thing for you. In case of asymmetrical vicinal diols, H2O will leave from that carbon which leads to stable carbocation. This is vital. Okay. So now migration of H plus will take place, H minus, sorry. So this is migrating. Shift and we now will get plus charge here, which will be stabilized, and that leads to the formation of a molecule like this. Okay, I think similar concepts can be used. This is a symmetrical one, this is an asymmetrical one, so try to use the similar concept and try to do these problems. Okay, I'm just showing this one because this is a little new for you. This is a symmetrical one, and here you can see we will protonate any one of them, and we can just cleave the bond, taking away H2O. Here is the positive charge. Now it was easy before when you had to migrate one group, so you cannot see any group over here, but you see one bond is here. Okay, one bond is here. Now if you had two bonds like the, any one of would migrate. Now you think if I close this part, so now either this carbon or this carbon can migrate. So if you migrate breaking this bond, so this carbon is going to attach at this point. Now what you need to do over here now is number the rings. So you place this as 1, this is 2, this is 3, this is 4, 5, and this is 6. So one of your rings, please understand, is a 5-membered ring, which is now joined to a 6-membered ring. This is your carbon 1, this point. This is 2, 3, 4, 5, 6. Now where will be your positive charge? From where this CC bond is breaking. So obviously my positive charge is over here, and this is my OH now. Lone pair is there. You take out a proton after that. So what will happen is something like this, this, this. This is basically a spiro, right? This is a spiro compound. So this is a spiroketone, as you can say. Okay. Now next. Will such rearrangements only occur when there is vicinal diol or there is something else? Now this is called Tiffenau-Demjonov rearrangement. In the alcohol chapter I have told you, or alkyl halide, that which is going to be your leaving group will depend what kind of reagent you're using. If you're using acid, then obviously water will go away. If you're using nitrous acid, This is called nitrous acid. This will lead to formation of diazonium salt. And diazonium salts of aliphatic compounds are very, very unstable. The moment they are formed, they break away. So NH2 gets converted into N2 plus. Plus charge on nitrogen is not stable. So nitrogen gas will go away, generating a carbocation over here, which now means that one R will migrate, and what will happen? This is R minus shift, you can say. It is producing R, R, OH. A double bond will form here. Okay, let's do it in the next step. Something like this will be formed, which now forms something like that. But this is not H, this is R. And if you take away the proton, again something very similar to Pinnacolone is formed, right? If your R is methyl, then it is forming Pinnacolone. Okay. I have given you some problems for practice. Okay. Now here also, if you are doing this thing, it is better to just to reverse the thing. This is your OH. This is your NH2. Just changing it. Now again, what will happen? N2 plus forms here. This is your OH. Okay. So this will go away because it is a very good leaving group. This is forming plus now. That is your OH. Again, number this as 1. The CH2 you number as 1. Call this is 2, 3, 4, 5, 6. Now if you migrate this bond over here, okay, so technically you're now forming again a 6-membered ring. You're forming a 6-membered ring where there will be a plus charge. So lone pair will come like this, and eventually will form something like that, which eventually will give you something like that. Okay. Just another extension or modification of the above problems. If you are given a bromohydrin, how a bromohydrin forms, you obviously know. Suppose you are given a alkene, something like this, and you treat this with Br2 in presence of water. Okay, bromohydrin will be a product. Technically, think HOBr is added. What is added? HOBr. This is your plus, this is your minus. Okay. Now, you know silver is a very good metal that forms precipitate with bromine. So AgBr will be formed and will precipitate out, leading to the formation of plus charge over here. Again, now these are all methyls. So think one of the methyl is again making a transfer or migration. Sorry. you have OH over here. This plus charge will be neutralized. Okay. And you have OH plus, just a similar thing, H minus. So something like that will be formed. Okay. I think we have covered all the things that we wanted to do today. Okay. Thank you for listening. Have a good day.